Okay, this is number 997 of LeetCode, Find the Town Judge. And this is an easy problem for the graphs category. So in a town, there are n people labeled from 1 to n. Um, there's a rumor that one of these people is secretly the town judge. If the town judge exists, then the town judge trusts nobody. Everybody except for the town judge trusts the town judge. And there's exactly one person that satisfies property 1 and 2. You're given trust, an array of pairs, trust I equals AB, representing that the person labeled A trusts the person labeled B. If the town judge exists and can be identified, return the label of the town judge. Otherwise, return -1. So we have our. Let's just. I'll just draw these out just so that it's clear what we're talking about. So, for example, 1 is going to 2, and then 2 is the town judge because it fulfills the condition that the town judge trusts nobody, so there's no outgoing edges. And everyone that's not the town judge trusts the town judge, so they have an edge going to the town judge. And there's only one judge that satisfies the two properties. For example, 2, we have 1 going to 3, we have 2 going to 3, and this also fulfills the town judge condition. The town judge has no outgoing edges, it doesn't trust anybody, and everyone has an outgoing edge to the town judge, so everyone trusts the town judge. For example, 3, we have 1 going to 3, we have 2 going to 3, and we have 3 going to 1. And this now is our previous example, but now the judge has an outgoing edge going to a non-judge, which nullifies it being a judge because the judge doesn't trust anyone. So in this case, we would return -1 since there is no town judge. For example, 4, we have 1 going to 2, we have 2 going to 3, and yeah, so in this case, we have no town judge because everyone is supposed to trust the town judge. So if basically if we had this going on, then 3 would become a town judge because all of the citizens trust the town judge. Yeah, but that's not the case for this example. For example 5, we have 1 going to 3, 1 going to 4, we have 2 going to 3, 2 going to 4, and 4 going to 3. And in this case, the town judge is 3 because everyone in the town trusts the town judge, and the town judge doesn't trust anyone. So putting that aside now, we have our solution here. And basically, we realize that the trust is a graph. The first number of every tuple is the starting vertex. The second number is the ending vertex. Every pair represents a directed edge. The 3 properties reduce to one condition. Basically, that there is a judge vertex that all the other citizen vertices point to, and this judge vertex, if it exists, will have in degree minus out degree equals n minus 1. So we'll have net degree of n minus 1, and the judge vertex is the only one that will fulfill this condition. And if there's no vertex that fulfills this condition, then we return -1 because there's no town judge. So our algorithm is just going to compute the net degrees for every vertex and check if there's any of them that equals n minus 1. This has time complexity of t plus n and space complexity of n. So we set up our count array, which is of size n plus 1 because we're using 1-based indexing. And then for ij in trust, we subtract from the net degree if that vertex is pointing to another vertex, and then we increase the net degree if other vertices are pointing to that vertex. And then we check if the net degree is equal to n-1 at the end. And if it's not, we return -1. So if we run the code, yeah. So there we go.